So welcome. I'm Stephanie. I'm your instructor, obviously. And so every week of class, I do one live lesson picking a topic in the class, basically, to go over some topic that you may be struggling on. My goal is to eventually have videos on every single topic for the week. And so that's sort of like what I'm trying to do is, each week I pick a topic that I haven't really done a video about, or maybe if it's a video that I have that I need to improve, I'll redo the topic. So it's your, one time a week that you get to have, a real class, ask questions in person, that sort of thing. It's not required. So, if you can't make it, I do record it and then I share the recording the next day. Just so you know, if you choose to speak, verbally, that will show up on the recording. So if you prefer, you can just ask questions through the chat. You can, chat with everyone, or if you feel more comfortable, you can always just individually chat me with Zoom. And yeah, so that's sort of how this goes. Now, normally I do start at the time on the dot. So, if it starts at 6 p.m. Central, at 6 o'clock Central, I will begin. So that's why I send a 5-minute warning, so to kind of log in and make sure you're ready. So if you try to, log into Zoom a little bit before the time starts, so that way you're all ready and it starts. And yes, if you're completely comfortable, you can unmute yourself and ask questions. Just, I'm totally fine with that. I just want you to know that any questions you ask verbally will be heard on the recording, versus if you ask your question through the chat, then I will kind of repeat the question. So, it's kind of just up to you on whether you don't care if your voice is on the recording, or if, whatever is comfortable for you. But I do expect you guys to ask questions, because, that's the advantage of having a live lesson, is that you can ask questions and, get help or whatever. But I do specifically have like a lesson, like a topic that we have. So, yeah, before we get started, let's see. I do want to show where the videos are. So let me share my screen. So right underneath discussions here, there is a link that says videos. And so you click there, and then you'll see I have it separated by week. And you just click on week, and then they're separated by homework. So there's 4 homework assignments, and then there's videos that go along with each one. So this can kind of help you. So if you're struggling on the homework, you can go to the videos that go with that homework to kind of, get some help. So I've got videos on, arithmetic, fractions, the order of operations, and this first one. These videos are also linked if you go to weekly content and then you click on your week. This link will also take you to those videos. So you can either get to the videos straight by clicking on videos, or you can get to it from the weekly content. So you'll find it both ways. And then the last place where I put these videos after I do the live is under announcements. And so I will, let me put it on student view here. Yeah, so after I do the live session, the recording will be in the announcements, and I'll email it to everybody. So you'll see it in the announcements underneath. So these 3 things are always here on top. The quick start will disappear after week 1. I just wanted to make sure everybody had that. And then once everybody knows, what you need to do, that will not be there anymore. And then this only shows up when we have a live coming up. But this will always be pinned at the top. Then underneath it, everything is in order. And so after the recording is all set up on YouTube and everything, you'll get an announcement and it'll be posted underneath here. So that's where you can find all of these recordings. So there's 3 places where you can see the recordings. So if you miss it, you're sure to find it. So with that, I will get this going. So the topic that I'm covering today is subsets of the real numbers. So this topic specifically goes with the first homework assignment, which I know there are some people that still haven't done that assignment. And it goes specifically with the first question on that assignment, because it's one that a lot of people actually tend to get wrong. And it's actually an important concept to kind of understand the different types of numbers, because there's a lot of theorems and properties that we'll learn throughout the term that will be relying on specific types of real numbers or certain groups of real numbers. And if you are in like a computer science degree or an engineering degree, you will, a lot of them have to take like discrete math, and that relies on different types of real numbers. You might be focusing on different groups of the numbers and not every single number that we know. And so it's an important concept for those that are in some more of the STEM fields. But it's also just good to have a basic understanding of the different types of numbers we have and the different names we have for those numbers. So we have the set of real numbers. This is basically the kind of numbers that we work with. So first off, when we say the set of real numbers, anything that is just a group of numbers is what we call a set. And sets are generally, oops, thought I had my pen going. Sets we indicate that we have a set with curly braces. So you may have numbers in between these curly braces to indicate that you have a set. And so the set of real numbers are just the numbers that we work with. And we have this special symbol, which you can see is like sort of like a bold R with double lines. When I write it by hand, I just usually do the 2 lines going down, and I don't make the whole thing double. We usually just do one of them if you write it by hand. But that symbol is just a shortcut to indicate real numbers, or the numbers that we work with. And so when you're taking notes, it's kind of nice to know that we have this special symbol that you can use, so you don't have to keep writing in real numbers all the time, because it has an actual special symbol. But the numbers that we work with just on a daily basis, we've got negative numbers, we've got positive numbers, there's decimals, the fractions, the kind of numbers that you can graph on a number line. That's what we call the real numbers. And so this is just, the numbers that you learned, they have a special name called the real numbers. So there are other types of numbers that are called subsets of real numbers, because it's just a smaller group. We're taking all of the numbers and we're putting them into a smaller category, so it's a subset. And so some groups we have are the natural numbers, which are positive numbers, but specifically we don't have any fractions or decimals, and we don't include 0. So the natural numbers are the numbers that you use when you start counting. 1, 2, 3, 4, and so on. When we start counting, we don't start at 0, we count at 1. So those are called natural numbers. And we call those the natural numbers because those are the numbers where you naturally start learning how to count, is you start with 1. So the shortcut is an N, and that's how I write it by hand. Is again, I just only make one of those. When you type it up, it has the double on the angle, but it's kind of harder to do that. So I just do the downward ones double when I write that by hand. But the natural numbers are only those numbers that when you're teaching somebody how to count. Then when we have zero involved, that's what we refer to as whole numbers. So whole numbers, which we can use W, and that's 0, 1, 2, 3, and so on. So you may be wondering, why do we have two different names for this? Well, we'll kind of talk about this a little bit in some of our discussions. I think just the week 3 discussion, you kind of talk about sets of numbers. But zero wasn't something that people normally had. You know, the first thing when people started doing math and counting, they started with 1. They didn't start with 0. And so that's why we have this special thing for natural numbers. So then once people realized that 0 was a thing and it would be useful to actually have a number for 0, that gave us a whole new set of numbers called whole numbers. Because, you know, the history of how math came to be is people realize, you know what, having 0 would be really helpful to recognize that we don't have something. And so just in the history of how we came up with different types of numbers, adding 0 came next. And so that's how we have the whole numbers. Then next we have integers, and that is where we are throwing negatives in there. So it's important. We refer to whole numbers every day, and we usually include negatives when we say whole numbers. But technically with math, whole numbers are only positive. Once you include the negatives, those are called integers. And the symbol for integers is a Z. And we use Z because that actually comes from the the German word that the German word for integers. I don't remember what the actual word is, but the Z actually comes from German. And so integers came next because, you know, we were learning our numbers and we're like, okay, let's, you know, 0 is very helpful to have. And then somebody was like, you know, it'd be really helpful to actually indicate when we're in debt. You know, when you owe somebody money, it might be helpful to have a way to indicate that you owe someone money, and that's where integers came in. So then we're like, you know, let's have this new thing called negatives. So yeah, there's a lot of I see comments, but this is really fascinating. Yeah, we have a discussion all about it, so you can pick one of these sets of numbers to like research and learn more information about it. But it is really interesting that it's like the whole history of math kind of follows these sets of numbers. And so then we are like, oh, we're going to throw in negatives. So now we have a new name called integers. You don't want to admit if you own money. Yeah. What is really interesting reading about negative numbers is that there was a really long time when people argued on whether negatives existed or not, you know, because it's like a whole thing where people are like, no, negatives don't exist. You know, we only have positive numbers. Negatives don't make sense. It took many, many, many years for people to accept that negatives were useful and made sense and actually added to what we do with math. So these are the 3 biggest sets of numbers. And if you have to take discrete math, you talk about integers a lot. A lot of discrete math just focuses on integers because you're just looking at whole numbers, basically negatives and positives. Then we have rational numbers. Okay, so German word for integers, ganze Zahl. So it must be that Zahl that comes from the Z on how they got that word for, I cannot pronounce German. I probably pronounced that very wrong. Zahlen. Yeah, I think that's where they came from it to count. That makes sense. So thank you, Georgia, for looking that up. I knew it was German. I'm like, I know that Z comes from German there. So next we have rational numbers. And so if you're following just the whole history of numbers, the next thing that people came up with were numbers that could be written as fractions, because people started realizing, well, how do I indicate that I have half of something? You know, you had to come up with fractions. So we call these rational numbers, and it has the letter Q, and Q comes from the word quotient. So that is why it's a Q. And the word quotient literally means fraction, or it means division. So that's why we use the letter Q to go with rational numbers. And so numbers that you can write as a fraction are considered rational numbers. And this actually also includes decimal numbers, because a lot of decimals you can write as a fraction. So like 0.5 is a rational number, but you can write 0.5 as 1/2. So when we say rational numbers, we define it as numbers that can be written as a fraction, but it includes decimals. And it also includes like whole numbers, because you can write any integer, any whole number as a fraction, because you can write it as over 1. So it's like we take all the numbers that we've learned so far, and now we're adding in more numbers. And most things are rational numbers. If you have any decimals, you have, it's a rational number if the decimal ends, or it's terminating, it stops, it doesn't go on forever. Or if it goes on forever, it has a pattern, it repeats. Because if it repeats, then it's something that you can write as a fraction. So the next thing in the history math was these rational numbers. So we've got a couple questions here. One, what is two-dimensional math? So I'm assuming when you say two-dimensional math, you're referring to X and Y, which is basically, I mean, all the math we do, we've got like X. Oh, Dustin mentioned it above. Let me scroll up. I must have missed that. Negatives didn't make sense in two-dimensional math. Okay. Dustin, can you explain what you mean when you're saying two-dimensional math? How imaginary numbers were invented. Okay. So I don't know if I would necessarily call that two-dimensional math, unless you're referring to imaginary numbers being graphing. We have imaginary going vertical and real numbers going horizontal. But oh, I see what you mean. Math used to be represented by using shapes. Okay, so what Dustin is saying about negative numbers is that they didn't make sense because a lot of math was done with geometry and distances, and distance is not a negative number. Whenever we talk about distance, it's always positive. So that's why negatives didn't make sense to the Greeks, because they did all of their stuff with geometry. That's how they were doing all of their math. So that's what Dustin means by two-dimensional, because you've got shapes, and so you're kind of drawing 2D things. And that's where negatives came by. But there were other cultures that did have negatives, like the Chinese used negatives because they were not doing their math with geometry. They actually did their math differently, more like algebra. And because they did it with algebra, they were able to do more with math than the Greeks did. Because if you're not tying your math to shapes, it doesn't matter if you have negative numbers, because they're just numbers. They're not tied to like something that has to exist in real life. So that's the 2D thing. Okay, the next question was about the line above a number and then terminating decimals. So a terminating decimal would be something like 0.25. It stops. You have a certain number of decimal places and it doesn't go on forever. So most decimals that you work with, those are terminating. It means that it stops. There are lots of different types of repeating decimals. So like one is if you have the line over it, and the line over it means that that number repeats forever. So if there's a line over the 6 repeats forever. And we use dots to kind of indicate that it goes on and it doesn't stop. It just is, that pattern. So that's what makes something a repeated decimal. So if it has a line over it, then you can write it as a rational number. I think that is actually equal to 2/3. So 2/3, you can write it as a fraction, but if you actually put it in your calculator, you're going to get all of these sixes. And I guess it's a good thing that I did more than 3 6s when I did my 0.6 repeating. But that's what a repeating decimal is. This is just it has a pattern. It will go on forever. And so sometimes we write all the numbers, and sometimes we'll put the line over it so we don't have to write all of those numbers. And then, yeah, terminating decimals like 0.25, that is equal to 1/4. So that is another decimal that you can write as a fraction. Yeah. Oh, I did 3 6s twice. I guess, should I put a 7th 6 in there so that we're not like calling the devil? Let's just add a 7th one there just in case. I just wrote 6s. I didn't even think about it. Are there any other questions on rational numbers, decimals, that sort of thing? On the day of a massacre, all you're referring to, yeah, the Valentine's Day massacre with I think, was the Valentine's Day massacre, did that include Al Capone? I think it was. Yeah, some history there for people who like history. A lot of things going on. So those are rational numbers, you know, in the history of math, we're kind of going through all of the history. And so once people are like, okay, fractions exist, we're cool with this, we get it, you know, it makes sense that these exist, then we have irrational numbers. So our book uses the letter H for irrational numbers. I'm not really familiar with that symbol. It's not really used a lot, but basically if you have a number and you can't write it as a fraction, then it's called an irrational number. So if it's not rational, then it's automatically an irrational number. And so these are generally numbers that repeat forever without a pattern. So pi is an irrational number because it goes on forever and there's no pattern. It never repeats. So it's a special number. It's an irrational number. Another one that we learn about in week 7 is E, which is Euler's number. And a lot of square roots. So like the square root of 2 is a special one. When you put that in your calculator, it never has a pattern. It never stops, but there's no pattern. So it never has a repeating pattern anywhere in there. And so that's an irrational number. A lot of square roots are irrational number. So regarding the history of sets, this was a big deal coming up with these things. And it was the Greeks that actually had a huge argument about this. So everybody knows Pythagoras and the Pythagorean Theorem, you know, from the right triangle, a squared plus b squared equals c squared. So Pythagoras is doing all these things with right triangles, and he found that he would have certain triangles where the hypotenuse wasn't a whole number. When you try to use a Pythagorean theorem, you get a hypotenuse that might have a square root. And Pythagoras believed that it was impossible to write a number without basically being able to write it as a fraction. He thought everything was a whole number or could be written as a fraction. No other numbers existed. And so the fact that his own theorem came up with numbers that basically were against what he believed in was a huge thing. There's a story that there was a guy, I think his name was Hippasus. I'm probably pronouncing that wrong, but there's a story that is probably myth, probably never actually is true, but it's said that this guy basically proved to Pythagoras that, like, look, there are triangles that exist with hypotenuses that cannot be written as fractions based off of your rule, the Pythagorean theorem. And they were so upset with the fact that he basically proved them wrong, that, you know, proved that irrational numbers existed, that the Pythagoras had this group of people that basically they were on a ship and they basically threw the guy overboard because they were so upset with him for proving that irrational numbers exist. So that's the kind of the story about irrational numbers, is like they really do exist. We all know that pi exists. It comes up in nature a lot, but it took a long time for people to realize and believe that those kind of numbers existed. So, okay. So Dustin's question about the Pythagorean theorem. So we usually write it as a squared plus b squared equals c squared. So we make the two sides squared equal to the hypotenuse. So you could write it as a squared equals c squared minus b squared. That is equivalent to the same thing. We just don't normally write it that way, but it is the same thing, Dustin. So you can write it as a squared equals c squared minus b squared. But normally we write it the other way around. Irrational to throw him overboard. You guys are great on the puns today. I knew I should have like found a math pun. I try to do math puns weekly, but I was looking for some Valentine's Day puns that I could try to send, and I didn't really find anything, but maybe I'll find one. So those are irrational numbers. They're special type of numbers, and it's like, well, they don't fit all the other numbers, so let's give it a new name. So this brings us to this little chart that is in our book. It's kind of like a Venn diagram. Now, Venn diagrams are usually, we think of Venn diagrams, if I can get my pen to work, there we go, where you have, come on. Let's try, oops. See if I can, there we go. So a Venn diagram is usually where you have two circles and then you have a thing that overlaps. And so you've got like two categories and then these things overlap. The set of numbers is like a really weird Venn diagram where instead of having things overlap, you have things inside other things. So let's look at the rectangle we have here. Real numbers are in two categories. They're either irrational or they're rational. They're one or the other. They can't be both. Now, if you're a rational number, you are also, so things that are rational numbers are also integers, also whole numbers that are natural numbers. So if you look at the purple box that we have categories within those categories. So natural numbers, those were the numbers that we count with. So let's say the number 2. 2 is a natural number. We count with it. It's also a whole number. It's also an integer. And it's also a rational number because we can write it as a fraction. So everything that is the natural numbers is inside the whole numbers, inside the integers, and inside the rational, which means that it belongs in all of those boxes. So we've got these rational numbers, and then we have a smaller group inside of it, and then a smaller group and a smaller group. So whatever's in the most inside is also part of the bigger groups. So numbers can fit in multiple categories, except if you're rational numbers. Irrational numbers only go in one category. And then Justin did mention imaginary numbers. We're not going to learn about that this week. You'll learn about them in a couple of weeks, but then that's an opposite of a real number is an imaginary number. And that's the last type of numbers that have been invented and thought about. So we'll learn about those in week 2 or week 3, I think. I can't remember which one. But this is the set of numbers, and these are the different names that we use. So the homework problem that people get struggled with, this is the first one in the first review, where you've got this Venn diagram kind of thing. And so when you do the homework in Alex, you may have different categories, different names that you have to name, and then you'll have different true or false questions. So it says, use the names of the sets to label the regions of the Venn diagram. So notice that this Venn diagram looks very similar to what we had here. It's just this one uses boxes, this one has circles. But the section by itself that has nothing inside of it, because there's only one category there, that's the irrational numbers. So we can label that one immediately, because irrational numbers have nothing in common with any of the other numbers. So That box by itself has to be irrational numbers. Now we've got these other categories, and it's best if you do inside out. And actually, because we've got integers, whole numbers, and rational numbers, the other option of irrational would be rational, and that's always going to be the outside box. So we can add those right here. So it's either rational or irrational. And so you just split your bigger rectangle into one or the other. And then we've got our two choices, integers and whole numbers. So you want to think about which has fewer numbers in it. Integers include negatives, positives, and 0. Whole numbers are only positives. So if you think about how big something is, there are fewer whole numbers than integers because we don't have negatives in there. We have fewer things included. So that means it's going to be in the smaller box. They're the smaller circle here because there's fewer of them. So we have whole numbers here. And then we have integers because every whole number is an integer because it's inside the integer circle. But every integer is not a whole number because some integers are not within that circle. So that actually, we look at that first true false here. Some whole numbers are not integers. That is false. Every whole number is inside the integer circle. So every whole number is an integer because it's inside that circle. So that's how you read this chart. Okay, and then, yeah, your questions are going to be different because they do random questions each time. Yeah, so you'll have different questions. And Dustin is asking about doubles. So for those of you in computer science, because that is very important. So in computer science, you have integers, and integers mean the same thing they do in math. The word double is a special computer science word to basically mean real numbers. So they just call it doubles because it's basically double the size of an integer, but it's essentially a real number. So and I know there are several people who go into computer science that, you know, have to take math classes. So if you see things like doubles, that's a special computer science term, and they don't necessarily match with mathematical terms. So computer science borrows some math terms and then throws in their own words, and that's what they do. So if you're in computer science and you see doubles, those are basically real numbers. So they're not integers. So, okay, so true, false, some whole numbers are not integers. We got that. Next one, some integers are not irrational numbers. So we have to kind of be careful when you've got nots going on and you're reading a sentence like here. So some integers are not irrational numbers. So not irrational numbers means that the integers are not inside the irrational number box. So that is true. The integer circle is not inside the irrational numbers box, but it says some integers are not irrational numbers. Well, all of the integers are not in the irrational numbers box. So this is false because it's not that some of them are not irrational numbers. All of them are not irrational numbers. So all are not irrational numbers. So when you have true or false, you have to kind of think about them. They sort of feel like they're trick questions with the sum, because you're like, well, some of them are not. Well, technically all of them are not irrational because they're not inside that box. Next one, some whole numbers are irrational numbers. So if whole numbers are irrational numbers, then those whole numbers will be inside the irrational numbers box, but they are not. So some whole numbers are irrational numbers. That is also false. All of these all are coming out to be false. All whole numbers are not irrational numbers, or we should say no rational numbers are irrational numbers. No, I said the wrong word. No whole numbers are irrational numbers, because the whole number circle is not in the irrational numbers box. Then we've got all integers are whole numbers. For that to be true, that would mean all of the integers are inside the whole number box or the whole number circle. But it's actually the other way around. All of the whole numbers are integers, but all integers are not whole numbers. So this one is also false. Now, when you do this one, you may get some positive, or you may get some true, you may get some false. All of these happened to be false in this particular question that I pulled up. They're all actually false. So some integers are whole numbers, but we can't say all of them are, because there are integers that are not part of the whole number circle. Like a negative number, like -2, is an integer, but it's not a whole number, because whole numbers are not negative. Okay, question. You think you marked the second one true and got it correct. Some integers are not irrational numbers. I would double check. If you think you got that right, I would double check that you got the exact same sentence that I did, because I would say that is not true, because all integers are not irrational numbers. There are no integers that are irrational numbers. So saying that there's some integers that are not irrational numbers would imply that there are some that are, and that is not true. So you may have very similar statements here, but they might be slightly different. And so you do want to be very careful with your wording here. They're not going to be exactly the same. Any questions on this example here? Okay, no integers are irrational numbers, and that was true, right? Yeah, so that makes sense. Yeah, so some would have to be false. Yes, this is assignment number 1. This is the very first question in mini assignment number 1. Yeah. I know a lot of people probably already did it, but some people may have just guessed true and false until they got it right, maybe not have actually understood what they were doing. So I thought this would be kind of good to go through here. This is one of the things that math teaches you, is like, you have to pay attention to every little word to make sure you're understanding it correctly. And you're kind of thinking through logically, working through, well, what does this really mean? And I find reading math out loud can help. If you're struggling to understand something, sometimes it just makes more sense to read it out loud than to try to read it. I don't know, something about saying it out loud seems to help. So there's no other questions on this example. I've got this one here. So we're going to try to categorize the numbers so you can get used to the different definitions. And I have that 0.6, the 6 repeating here with a line over it. So we have a set A, and it contains these numbers. It has -3/2. the square root of 11, -4, 0.6 repeating, 0, square root of 9, and 1. So our first question, are all of the numbers in set A real numbers? And that is true. All of the numbers here are real numbers because all of the numbers that we know are real numbers. Good, you guys beat me to that. So next is all of the rational numbers. So this is numbers that can be written as fractions. And so when it says to list all of the rational numbers, we still want to put it in a set. In a set. So we've got -3/2. Square root 11, if you put that in your calculator, it gives you a decimal, and those square roots, basically if the square root does not come out to a whole number, it's irrational. So that's going to be an irrational number. -4 is a rational number. We can write that as a fraction. 0.6 with a line over it. That can be written as a fraction. I actually did that one earlier. Because that is equal to 2/3. 0 we can write as a fraction. Square root of 9. When you do square root of 9 on your calculator, that gives you 3. 3 is a rational number. So that means the square root of 9 is a rational number because we're looking at what happens when you actually simplify it. So because it simplifies to a whole number and we can write that as a fraction, that means the square root of 9 is a rational number. And then 1 is also a rational number. So people get kind of stuck with like those square roots and like the decimal things. So square root of 11, when you put that in your calculator and you use your square root button, I'm going to do that right now, you get a decimal that kind of does not have any pattern in it if you look at it. 3.31662479. There's no pattern there. The numbers don't repeat. That means it is not a rational number. So if you get a square root or a cubed root or any kind of root like that, and you don't get like a pattern with your numbers, it's not a rational number. So that meant square root of 11, not a rational number. Yeah, it's kind of like pi. Now the square root of 9, when you do that on your calculator, you get 3. That's a whole number. So that's a rational number because all whole numbers are rational numbers. Square root of -9. So if there's a negative inside there, that would be an imaginary number. But we have not learned about imaginary numbers yet. So the square root of -9 would be, we would say, not a real number. So that would be a whole different type of numbers that we have not introduced yet here, because it's not a subset of the real numbers. So next is list all of the whole numbers. So whole numbers are only the positive ones, and whole numbers do include 0. So that is just 0. It includes the square root of 9, and it includes 1. It includes the square root of 9 because the square root of 9 gives you 3, and 3 is a whole number. So when you're listing the whole numbers, we have 0, 1, and the square root of 9. Now the natural numbers, those are the numbers, the counting numbers. So what would be the natural numbers in set A? Okay, we've got an agreement that 1 is a natural number. square root of 9, because the square root of 9 is equal to 3. Oops, I wrote 3. The square root of 9. Yeah, so 3 is a natural number, but if you try to write 3, it would get marked wrong. They want you to write square root of 9. And actually, that's it, because 0 is not a natural number. So 0 is only included when we're talking about whole numbers. It's not included when we're talking about natural numbers. And natural numbers are only positive numbers. Only positive and not 0. So this is where it's kind of, you want to maybe have the definitions written down somewhere, because it's very easy to get kind of confused and be like, which ones fit into these categories? So next we have the irrational numbers. I dropped my pen. So irrational numbers are the ones that are not rational. So you just look at, okay, which ones did I not put in the rational number set? And those are irrational because they don't overlap. So the only one that we had that was irrational was the square root of 11. So that's the only irrational number we have. And then list all of the integers. So what would be all of the integers? And integers are the positive and the negative. So we've got some overlap there. When I do the integers, I'm actually going to start with the whole numbers that we have, 0, square root of 9, and 1, and then look for integers that are the negatives, basically, that are whole numbers. And that would be a -4. And that's the only one that we can add in. So integers, we don't have our even though we have a -3/2, it's a fraction, not a whole number. 3/2 is -1.5, so that's not an integer. So the only other negative that we have to add into this is -4. So those would be the integers: 0, square root of 9, 1, and -4. So it's kind of hard to, to categorize these things. It takes some getting used to the definitions, but it's really important to understand the definitions, especially rational numbers, because we're going to be using the word rational a lot throughout the term. And integers, we use that word a lot coming throughout the term, and irrational numbers. So what is an integer exactly? So integer are the whole numbers and the negative whole numbers, essentially. So no fractions, no decimals, just those whole numbers, either positive or negative, and then we include 0. So if I go back to my number line that I had, the numbers labeled here on this number line are all integers. Because we have only the whole numbers, positive and negative, labeled there, and 0. We don't have any like halves or anything like that. So those are the only, so those are integers. So in a fraction, only if it simplifies to a non-fraction. That is correct. That is an excellent question. So something's an integer if the fraction simplifies to a non-fraction. So let's see. I'll go to here. So an example of an integer would be, and then I don't need my highlight. Negative, oops. Negative, why am I yellow? Okay. -4/2. That is an integer, because -4 or -8/4, that's a good one. Yeah. -8/4. That simplifies to -2. So that's an integer. Even though it doesn't look like an integer, it looks like a fraction. we're looking at what happens when you simplify it, and it simplifies to a whole number, a negative whole number, and so that is an integer. That's a good example. Yeah, so Dustin is giving us an example including the absolute value. So the absolute value basically makes things positive. So you could define an integer, and for those of you that are not very good at math, you may just want to say, okay, this is too complicated for me. But there is a way that you can write integers using set builder notation, which we do talk about this week. And if I write it really mathy, it's going to look like this. Actually, whole numbers, I should use their whole number symbol, which is that W thing. So it's just the number where if you take the absolute value and it's a whole number, then it's an integer. That's what this very, very mathy thing is saying here. That's how you can define integers using math symbols. But I usually just say it's positive and negative in whole numbers, because that's a lot easier to understand than this math symbol stuff, where you've got like absolute values, you have this E thing, which stands for is an element, you've got your W symbol, you've got this vertical line, you know. So are there other questions on the different types of numbers and that sort of thing? Okay. Cool. So I will just stop the recording right now.